So welcome to the second lecture on the attractor dynamics approach to vehicle motion planning, a very long title here. So the sub-symbolic approach, I'll explain in a moment what that means. So far we talked about, behavior dynamics, it's a general term, but how to generate time courses of planning variables, behavior variables, here the heading direction of a vehicle. And the way we talked about it was that we plan these time courses by taking into account constraints that come from targets and obstacles, a particular heading direction toward an target that we want to achieve, or a particular heading direction we want to avoid. And in a way, so one could say that's symbolic in the sense that there is something we call a target, and there were supposed to be maybe 1, 2, or 3 obstacles, and they were in some sense really objects. You could say this is obstacle number 1, this is obstacle number 2, in the sense that they were adding contributions to the equation. And so every contribution has its identity. Next moment in time, you would again add the same contribution, maybe with updated parameter values. So that you could say that then the term in the equation stands for something out there, stands for an object. Symbolic might be not the exact right term for that, but that's how we named that a very long time ago when we first came up with these kind of ideas. And this is something that has been done a lot in classical autonomous robotics, when you have world maps, and in the world maps you enter objects with certain properties. You say there's a chair, there's a table, I'm going to act on those, for instance. But for this vehicle motion, it doesn't really matter. We really just want to stay away from obstacles. It doesn't really matter that we know it's this object versus that object. And in fact, we looked at the cases when the obstacles are magically close and we were avoiding both of them. So then for that purpose, it didn't really matter if these were 2 objects that were close to each other. It's just one big obstacle object. I already hinted at that when I showed you this run from a actual implementation of the approach. For the target might be a little bit different. Maybe you have a unique target. Now I have someone ringing the bell here. Edit that out later. And I'll not go very much into that in this lecture, but in the second lecture, you will see we'll do something about how the targets might just have some target information and not really be able to say it's an object, the target. Now, the one problem with that is that the requirements for perceptual processes to deliver such information are actually costly or important. It's not trivial to be able to segment the world into different objects and extract pose parameters about objects like that. And when we implemented this on this platform, actually, I hinted that was a problem, right? We would take a lot of readings, like distance readings, but we didn't really know if these readings come from the same object or come from different objects. And you could ask yourself, is it actually really necessary to solve this non-trivial problem? Because as I hinted, we just want to avoid a direction in space. We don't really care if there's 1 or 2 objects there. So I'll gloss over the target information. In the winter semester, those of you who listen to that or will listen to that, you might know that we're actually using neural dynamics to extract target information from some sensors. Now, the notion could be that what we really want to do is really just say we probe space, and we just want to avoid directions in space that are not sufficiently free, where we can't really maneuver. And again, we don't really care about how come that there are obstructions. As long as there are obstructions in certain directions, we want to avoid them. So an idea would be to have sensors, and these red buttons here would be such sensors that sense free space. For instance, there are distance sensors, and they could sense whether there is something in a certain direction that could could be an obstacle that sticks out from the ground, and then just avoid those sectors in space where there are problems like that. And so that's what we call subsymbolic, because it's really represented in terms of the sensor. So if we had like continuously many sensors, then we would actually not even have anything discrete. In practice, we'll discretize that by just having discrete different sensors, but that's just like numerical sampling of a continuous space, the space of heading direction. So that's where the subsymbolic notion comes from, that it's really a sampling of a metric continuous space. And in practice, we can use fairly low-level sensors meaning sensors that just receive a signal that don't do a real or don't necessarily enable a reconstruction of the world. Remember, in this introductory lecture, I said, perception is really about estimating the world, not about just processing sensory information. And here, low level would mean that we don't need to do a lot of processing. We just might need to map a sensor reading onto an estimated distance that is free. The distance up to which we know there are no obstacles. So that's what we'll do. I'll show you an example later. And we'll have, so in one project that this is work that Estela Bischu did, and I'll give you a reading from her. She's actually here in Portugal, where I'm right now, a professor in Guimarães, who's continuing work, not exactly like that, but work along similar lines. And so she built a robot. I'll show you some physical examples later, on which she mounted sensors. There were 7 distance sensors mounted on the vehicle. The big arrow is the forward direction of the vehicle, so the 2 motors would be on the side. And so these sensors sensed distance in some way. The different implementations would be different sensors. One example would be a infrared light that is sent out, and you measure the amount of light reflected back, and that would decrease when it's reflected back from a surface that's further away. It has a certain directional sensitivity. Oops. And then the notion would be that we would say every sensor is sort of like an obstacle, that it votes for avoiding that direction, the direction in which the sensor points. That would be this angle. Let's say if I'm talking about the sensor 5, it would be this angle, the sensor in which the sensor points in the world relative to that fixed world axis. And you can compute that from where the sensor is mounted on the vehicle. That will be this angle here. That will be theta. And the current heading of the vehicle. So if you add that angle on the robot to the heading direction, you get where in the world this sensor is heading. And then you would erect a repeller in the direction in which the sensor is pointing, with a range that reflects this angular sensitivity of the sensor. So if the sensor has some kind of cone within which it detects distance, then you adjust the range of the force that to be according to that. And I'll show you some more details about that in a moment. And then the notion would be that the slope of that repulsion, so how strongly you're repelled, is a measure of how far, how much free space there is. So here's the mathematical formulation of the forcelet itself. So we have a positive linear function centered at that heading direction, and then we'll get to that will be the slope. We'll get to that in a moment. And the range would be implemented, for instance, by a Gaussian, and the width of that would be sensitive to the cone of sensitivity. And we'll look in a moment at how to estimate that. One important observation right away is that in this expression, all the heading direction dependence is already written down here. And look, in these terms, the heading direction always shows up in combination with the direction in which the sensor is pointing, right? This always shows up as a distance here from the repeller. So phi minus psi, and here phi minus psi. Phi minus psi is the angle at which the sensor is mounted on the vehicle. So it's minus that if we, we can figure out, use the same conventions I used here. So we see here So phi, or let's say minus psi plus phi, that is this angle here. That's this constant angle. So in other words, these two terms here are actually constant for every sensor. It's a constant. It doesn't really depend on the heading direction. No? And maybe as homework, where we think about what happens to the front sensor. I think I have that question on the exercise sheet actually that I'll upload, where that angle is 0. So the real beef that makes this a interesting approach comes from these constants here, the parameters like the slope and the width. Right? The strength here is made a function of the sense distance. So the assumption is that it falls off exponentially, for instance. It's a very nice parameterizable form. Falls off exponentially with the distance, so that if you have a lot of free space, then this is a very shallow repulsion, ultimately negligible, no repulsion. So on the scale of a parameter, that's the spatial scale, you can say it's anything that's beyond a certain scale. For instance, that's maybe measured in terms of the size of the vehicle. Do you have enough time to still maneuver? Then you would neglect any obstruction in your pathway. So that's really where the sensory data enters. The other factor is how broad that range of repulsion should be. So I hinted that very naturally you want to have a width that reflects the sensitivity range of your sensor. For instance, here, if you have a sensor that has a certain sensitivity cones written down here as delta theta, then you want to make sure that you're at least avoiding that sector. And then you, to exactly compute that, and that's here, these inner lines. That's supposed to be something physical about the sensor that tells you that sensor will record any distance that is caused by some surface, some obstacle within that cone. But then you have to avoid that whole sector, and that will mean that when you're at the sense distance, your vehicle has to fit here. So it would be like half your vehicle width would be added here to this at this end, and half of it would be added here at that end. And that makes that cone actually, again, distance dependent, because the safety margin in angle that you need depends on how far the obstacle is. Remember, imagine if you're closer than the angle subtended by the vehicle as it is passing, added to this cone would be a larger angle. I wonder, would be a larger angle. Like at this distance, you would have to add a larger angle, and therefore the angular range that you should avoid when the obstacle is close or the sense distance is small is larger than when the object is far. That actually makes a functional difference. We'll come back to that. So we figured out this particular functional form by knowing the robot size. So this is the sensor cone, and this is this angle subtended by the vehicle when it is positioned at distance di. You can go through the geometric equations, figure that out. The arctan of that is this outer sensor cone that I'm showing here. So that's where, again, the sensory data enters, the sense distance enters also into this second factor. So we have it show up in the strength and in the range. And the zero crossing is just fixed by where the sensor is mounted on the vehicle. Okay. So what you then do is just add all the contributions. That is, you simply consider every sensor to be an obstacle in a sense, and that's why I'm saying subsymbolic, because the sensor are just samples, and so you don't have to have that these are different objects in the world. They are just sectors of the heading direction space. And here in this case, we had 7 sensors, and you add up. So here's an example. Here only if you have this kind of situation, actually a lot of these examples I show now come from actual measurements on the vehicle. And so in this case, only 2 sensors actually had a obstacle that they sensed. All the other sensors, any surfaces were at a larger distance than the sensor range. Most of these sensors have a limited range over which they can sense distance. And therefore, we had only 2 contributions, psi 5 and psi 6, these 2 sensors here. And you see that their repulsive forcelets are superposed, so that the repeller is sort of in the middle between those 2. So you would be having here a repeller that goes about in this direction, and we tune these parameters that the what is being avoided is something that goes about plus minus 180 degrees from that direction. So you would be pretty much avoiding something almost, this would be like maybe the left and that would be the right, or actually the other way around, left and rightmost boundaries of the range of repulsion. If you look about here and about here. So that's how that works. Now, you might wonder, this is sort of the one subtle point about that, and I'll invite you to think through that on the exercise sheet. You might wonder why that actually works, because we made a real point about the behavior constraint not depending on the current value of the heading direction. But here, if you rotate the vehicle on the spot, it would depend on the heading direction, right? Because the sensors are pointing in different directions when you are rotating on the spot. The sensors move with or rotate with the vehicle, and so you could wonder, well, that would mean that the repeller shifts as I rotate, and then that would mean that the dynamic that I erect that way would not actually be consistent. That is, the zero is moving with the vehicle. So for instance, if you, let's say, let's just pay attention to, I'm going to just always have the same scene. Here's the same obstacle, and looking at a case here marked by red where the sensor 5 and 6 sense the obstacle and the vehicle is sort of pointing this way. That gives rise to this dynamics that I just showed you, and the heading we currently are at is about here near sensor 4, which would be about here. So this is the value, this would be the turning rate you would have in this particular configuration. And so if you now look at the same situation, but the vehicle has rotated on the spot, now you have different contributions to dynamics. So for instance, now sensors, I think 4, 3, and 2 hit the obstacle. So you have 3 contributions, 2, 3, and 4. And so it's different. So the individual contributions are different. But you can already see that the superposed contributions look somewhat similar to what you just saw. I'll show that again in a moment. And we're sampling that with the current heading, which is again at sensor 4. So at the blue line, which is a different heading. That's natural because we are pointing to the obstacle. So now we're turning in, for instance, to the left to avoid that. So here, the two situations superposed on each other, on the same figure. And again, you see that the individual contributions to the dynamics really are different. So so if you change heading, then the dynamics of these individual contributions is different. But if you look at the black line, then you see that that isn't very different. This is actually not exactly invariant. It is slightly different, as you might see, but it is roughly invariant. And invariance means that it is really a consistent dynamics. That is, what I really need to do is that if I'm here, then the fat line tells me the turning rate, and if I'm here, the same fat line here tells me the turning rate. Right? So the turning rate really depends on the heading, as described by this equation. Unlike for the individual sensors, you could say, let's say here the sensor 5, then I would have at this location, I would have this particular value, and at that location, that value. But as you see that when I'm actually here, the sensor 5 doesn't even respond. So there is so the individual contribution is not invariant, and therefore the individual contribution is actually not a consistent dynamics. Only the superposed contributions form a real dynamical system where the heading, the turning rate is really a function, a well-defined function of heading. See, that's where this, previously you might have thought, well, what does it mean that the dynamics is invariant? And here you see it's actually not trivial that that's the case, right? That as you vary phi, the rate of change of phi only changes in the way described by the dynamics and not in some unpredictable other way that comes from the sensors sensing the world. Yeah, so this works because of that. So the invariance is not perfect, and one can do something numerical about that, but it's comes really from measuring the width and the strength and so on in meaningful ways. You can tune the parameters of the system, these beta parameters, so that this variance is good. And we've in our modeling work, we've always checked that that's actually true. There's a whole range of such values where this invariance is approximately correct. So that's how that works. Now, the integration of the other behavior is straightforward. In fact, the target in this lecture will not really be solved. It's still symbolic, right? We have a tar contribution. So we say somehow there is a direction in the world that is the direction of the target. And in the implementations, it's actually in coordinates. We have some memory for where the target is, and we use that reckoning, estimating where the robot is, to always compute in which direction the target must lie. And we have other approaches. You'll have a chance to see that in papers that I'll ask you to read, but I won't lecture about that. Approaches how to use that information to estimate where the target lies. So here you see that classical example we had for the symbolic approach, where the target lies in the direction here roughly of theta 4, I believe. So it's the dotted line here that would want to push the vehicle into this direction, and tractor here. But there are obstacle contributions from sensor 5 and sensor 3, I believe. And I don't actually remember which is which. And you see that some of those makes a repeller in that direction, and the attractor is about almost 180 degrees away from that. So this would be probably some direction here toward the bottom, going around these obstacles. There's another attractor on the other side that's going around this way. And again, remember, I always switch the axis. So one goes around this way and the other goes around that way. So that's the same integration that we had before. I want to show you some cool dependencies. You can now really sort of see these bifurcations work. So I'll show you a couple of examples that we discussed previously. Now with this really with this sub-symbolic approach. So what was seen here, two plots. One is just the obstacle contributions here, this top plot, and then the second is the target added. You see the target is this dotted line, and then you get the fat line as the superposition of all the contributions. The dashed line here is the same as here on top, which is just the obstacle contribution. In the obstacle contribution, you see the individual obstacles, the individual sensors contribute. So for instance, here you have a wide opening between two objects, and only sensor 2 and sensor 6 get a reading. They make repellers. Here's a repeller and there is a repeller. And these are far enough from each other so that in the middle, there is an attractor that just comes from these sideways of the repellers. So this, even without a target, the system would actually go through here between these two obstacles. If you add the target contribution, you see the dotted line has a -0 crossing here in between. Then the attractor becomes actually even more pronounced as an attractor here, right? Going through the middle. While if these two obstacles are close, then 4 sensors hit the obstacle. Number 2, 3, 5, and 6, see, they're quite different. The effect of those is to make one big repeller here in the middle. And there is the attractor essentially in the back. You can go away from these obstacles. If you add in the target, you make sure that the slope of the target attraction is sufficiently shallow, then it cannot overvote the repulsion. So you have a repeller in the direction of the target. And you still have only an attractor that's actually very flat, sort of very soft. It's a whole range of attraction in the opposite direction. So here you would be heading away from this whole configuration. And then as you head away, we'll see that then things are going to change again. So that's the bifurcation from an attractor to a repeller. That's what we looked at earlier. So as you vary the distance between the obstacles, you can literally do the pitchfork that we had previously looked. This is, again, a situation where everything is symmetrical, as we have these obstacles in a symmetric configuration for the vehicle. So it's really that they really meet this way. This is done numerically on the vehicle. We took readings from the sensors. That's why these data are a little little variable here. And so we see here the stable states colliding then to a single stable state when they're sufficiently far, these two obstacles, and there is the unstable repeller in the middle. There's also the sort of the attractor on the, there's actually a repeller on the back in the opposite direction in some of these cases. So empirically, you can use this kind of diagram to tune some of the parameters that I'm presenting at you. There's actually only a very limited number of parameters, these the beta factors, that go into how strongly the distance depends on how much the strength of the repulsion depends on distance, and the fall off and the offset of that. So here's an example of that robot actually working. The robot is essentially a computer on wheels. I showed this robot in a different context in the winter semester. The sensors we're using here are barely visible. These big black things here at the bottom are sonars, which we also used in some cases, but currently it's not running on the sonars, it's running on a small light LEDs, light emitting diodes, and there's a little receptor on the same mount here. It's just above the black thing, and they sense really obstacles or distances only indirectly through the amount of light that is being reflected in the infrared domain. Here, Pierre Mallet, who is the engineer who built this thing, helps the robot a little bit to find back to the target. The target is here, and the robot knows about the target only by dead reckoning. We have pretty precise servo motor, so its dead reckoning was quite reasonable. Dead reckoning is integrating the motor commands to estimate where the robot is. So we use these white cardboards because those have a very nice reflection of the infrared light. So this is not a calibrated sensor in that the amount of reflected light will depend on the surface color, maybe also the how continuous the surface is, but it's a fairly good approximation. I'll show you a couple of examples. This robot works astoundingly well in laboratory experiments. So this sequence reproduces what we showed in the what I showed in the plot. There is no opening, and then a little bit of an opening, right? It still turns away, and then if there's a large enough opening, it goes through. Here you see a little bit of an oscillation, right? You see this little. By the way, the keyboard was just put on top of that. That's not really supposed to be the cover. Later, we had an infrared keyboard, but at the time, this is like 30 years old or something like that. So at the time, everything was clumsy. This oscillation actually has is a well-known phenomenon. Many approaches have that. Sort of it comes from the fact that when you're turning a little bit in this direction, then you don't see this repulsion, and then you might want to turn again more toward that. And as you turn, you then get some sense of reading on this side and so on, and reversely on the other side. But it's not a big problem. Other thing I want to point out in this simulation is that it's only a local approach, right? This approach tells the robot, now you can't go this direction, and it goes away. And as it goes away, the influence of these obstacles goes away. So now behind the robot, so it doesn't even notice that, and even after turning, doesn't have a strong influence because the distance is large. The robot doesn't really have a global plan, so it is attracted back to the obstacle really just in terms of angle, right? It can turn now because the obstacle has a smaller influence, and then it only knows the direction to the target, doesn't know that there's an opening here. So in one case, for instance, here, I think this case, it turns in this direction, so it doesn't know there is no opening here. And what it really would do is wander around here for a while to ultimately turn, and Pierre Mallet was kind of making a shortcut by presenting himself there so the robot doesn't venture out to fight. I don't know, maybe there was something here he didn't want the robot to run into. So it's a local approach. I'll comment on that in a little while. So here is really the bifurcation in real life in a way. I just want to make this sort of drives home the point we made last week about the system tracking the attractors except at the bifurcation. So, we're looking at the dynamics at 3 different moments. They're quite close in time. So here, this is the critical moment where something happens. So it's still heading to the target, and then you see that it will be turning. And so this is a little later, and this is just where it starts to turn, right? These are 3 moments in time. And in each case, you see the obstacle contribution and the sum of all the contributions. And you see here initially no obstacles detected. These are quite short range, these sensors. And so you just have the attractor at the target direction. And then if you're a little closer, the obstacles start to be sensed, and you have a little positive contribution. And you see that these two are about the same in size. So it's sort of flat now, still sort of heading in that direction. A moment later, these actually the gray graying here of these lines indicates that some sensor reading has taken place. Now 3 sensors actually sense the obstacles, and you see a stronger obstacle contribution. And now that stronger obstacle contribution has made this already a repeller. It's initially not very steep, so it's just about repelling. And then, but enough for the robot to actually now switch to the attractor, which is sort of in the back direction. That's how it will ultimately make this turn. So the bifurcation happens pretty much around here, right? This is where it's flat. And this is the same kind of sequence, but the obstacle is a little further away. And also it's just these 3 moments in time just before, at, and behind the repulsion and attractor. Here it becomes flat. And here it is, I think it is already a repeller, but a very flat repeller. So it takes a little longer to turn away. And there's an attractor here, another attractor here. So I have the 2 directions in which it can turn. And here, finally, this is a case where it can go through, and you see as these 2 sensor readings contribute, the repulsion from these is not enough to turn the attractor around because they are sort of off to the side here. And then even if it's in the middle here, it always retains the attractor, so it goes all the way through. Oh, that's okay. And so this example illustrates concretely how you're tracking the attractor, how when you go around and you have different dynamics. So again, we're looking at the same configuration, and the path was put in here to orient. And we're looking at this moment in time versus that moment in time. So at this moment in time, these 3 sensors sense some obstacles. So we have these 3 curves here, and you get a nice strong repulsion around the direction, in the global direction of these obstacles. They're close enough for those to overlap this way. And then there is an attractor sort of on the back of these obstacles, while the attractor toward the target here makes this negative slope. And here it's overturned. The sum still has a repeller in this direction. And that's how this makes actually that the vehicle is currently turning, and we'll see in a moment the time course of that, toward the attractor that's here on the back. There's actually a broad range where it could be moving in the back direction. Now, after turning, a little later in time, the dynamics has changed. Here you see that in terms of the sensor reading, there is this arrow is, by the way, where the heading of the vehicle currently is. And you see that now there is a repeller in a general direction, sort of in this general direction. But the sum of the repulsion and the total force that is actually makes an attractor exactly in this direction. So the system is actually very close to the attractor right now. And this is a similar case. Let me just a little more briefly. 2 moments in time as it moves through, and you see that the obstacle contribution changes quite strongly. The angle, because now when you're close to an obstacle, the angle of the bearing of the obstacle moves quite quickly. But then the dynamics, near the state of where the dynamic is, which is really heading here in the same direction, you see that there is not so much change. And this, in these 3 situations with narrow, so very close, medium and large distance between the 2 obstacles. And what we're plotting here is all the attractors in the dynamics. So we have the sensor readings. From that we can compute the dynamics, compute the attractors numerically, and keep track of them. And so this took recorded data from the vehicle as it was doing these moves. and then plotted the different attractors, and the thin line here is the actual realized heading direction of the vehicle as a function of time. You see, initially there is an attractor toward the target in all cases, and in the case when it's wide, the vehicle goes through. You see the attractor shifts around a little bit. This when it goes through the opening, then there are these distance readings, and those fluctuate a little bit. You see a little bit the oscillation. There are some other attractors which lie in the opposite direction, and they're sort of going around the obstacles in a different way, but they're not reached. They don't really affect the system. While in the other cases, you will see a real bifurcation. You can literally see the pitchfork in that the attractor splits. Let's take this case, which is sort of clearest. You see a split of the attractors into going around one way versus the other way. And you see it does take some time for the actual realized solution to go away from the former fixed point. There's still a repeller here in the middle, and it needs some noise, which we actually actively add to the equation, even though there's also sensor noise that would act in this way. But we added noise to all our dynamics always to make that the escape from a repeller is in a way more deterministic. That is, you quickly move away from the fixed point itself, and then the dynamics pushes you away. So it takes a little bit some time, and therefore there is some risk of constraints violation in this period when you have a transient, we're not in the attractor. And then the system relaxes to the attractor, and then you see it does track the attractor as the attractor moves around. So this is a case where it's really very symmetrical, where you see that just as this attractor moves down, the other one moves up. While here you see that there's a little bit of a gap here. So this is probably where there is a tangent bifurcation here at the bottom. The repeller, which is not plotted, would collide here with this one, while there is another unrelated attractor on top. And that's also something that very typically happens. So this is just a couple of scenarios in this. So this is the target. And you see that this is the case where it moves out here really surprisingly smoothly. Remember, this robot doesn't really know anything about the room plan, just really goes in the direction of avoids obstacles, avoids these wall obstacles. And see it moves very cleanly. Here we started, now this is the target. See, it tries to go straight to the target and goes around. Again, this robot doesn't know where the world is. For instance, it didn't know that this was maybe a shorter path. And I'll comment on that in a moment, but just watch that this thing actually does find the opening. It's not a very cluttered environment. And these paper boxes are very good for this, for the sensor. So it finds the opening, right? Because essentially it does something like wall following. If there's a wall, these are all obstacles, and it does that well. And so, yeah, I have a text slide, yeah. So it looks like it's solving global problems, but it's just purely locally because it's sort of emergent from the structural environment. I'll show you an implementation in a moment where we exploited that. So here we blocked off that wall, and the robot finds the other shorter path. No, not because it knows, it's just emergent, because it was initially heading in this direction, it would be normally running along the wall. But with that additional obstacle, it actually finds the alternative path. So this very low-level approach solves some global problems. It's so surprisingly good. It's some form of emergence, we like to call that. And that emergence comes from the fact that you have these continuous walls that act as obstacles, and they offer enough sensor information so that as you move, there's always a obstacle that is constructed, in the subsymbolic approach, constructed by the different contributions. And these are not crazy conditions. So Pierre Mallet, who was the research engineer working with me in Marseille, built this wheelchair version of the program. He has a patent on that. Actually even tried to bring it to market, and we had some difficulties with that were not technical or scientific, that were actually commercial. So what we did is we mounted on the robot a lot of these sensors. You see, all these are sensors. Actually, we bought these LEDs. can only buy like 1,000. Everyone like it's 5 cents for one of those. And so the minimum amount you had to buy was 1,000. And so we had a lot of these sensors, and we built little. We had little chips where we put, I think, like 5 receptors to increase the sensitivity and sense a little larger distance with every emitter. And we put that all over this vehicle. The vehicle is not actually it's not, it has holonomic constraints, so it's a little bit more complex in navigation. But we approximated that very simply. And here, this is just a demo with a laptop controlling this. And the idea was that it would do obstacle avoidance, and you would just give it a target in terms of its current position. You say, you know, like 5 meters ahead and to the right. So, for instance, users who have some motor difficulty and can't really continuously control the joystick. And if you can control the joystick, then you want to move with the joystick, which is really fun. But if certain people with spastic difficulties or other kinds of difficulties cannot really do that, but they can intermittently enter a target in through, for instance, certain interfaces that are built for such people. So some people, for instance, we built a little interface where there is a map of the building which they are, and they can some way select a room, and then this vehicle doesn't actually have navigation, doesn't know where it is. It's just the user who tells the robot, you know, relative to where it currently is, what the nearest goal is. And then that's just a heading direction to the target. And the walls in an apartment serve as obstacles that guide the robot along the wall. So here's an example of this, of course, in our lab. I don't remember if we have some. I have some other videos, which are maybe not here, where we're actually navigating along walls in the building. Yeah, here. So here, for instance, this was the lab room, and now it's actually going through relatively narrow corridors. And you will see in a moment that it does. This is a different run, just the same scenario. See, going through the door is a kind of tricky thing. It's all just done on this low level. So there's nothing, no algorithm that computes turns or anything. It's really just this very low level thing. Also has these oscillations sometimes, and goes along the wall, and it actually ultimately finds the opening here. We gave it a target just through the wall, and the wall, you know, as an obstacle, the wall essentially makes wall following if the target is inside the wall. So it finds doors because you essentially find a target inside the wall, and so it will be pushed away from the wall by the obstacle avoidance. And as soon as there's an opening and the obstacle avoidance stops acting, then it will be going into that room. We also controlled the speed for some reason, and I'm not explaining that. That helps us with these turns here. And so, for instance, here it ultimately finds, I don't know where these videos end. Does it have, no, actually it tells you how far it went, yes. So we did a clinical test in a rehabilitation center for people with these difficulties, and they really loved it. And especially a pity this wasn't commercialized, because, you know, people who are not able to operate their own wheelchair will be sitting around forever until someone moves them. So, and it's very boring. And with that, they can move a little bit. It's still not, you know, the alternatives are the very, very expensive systems that map the environment, and that you have a real navigational approach and so on. And that is much more expensive and much more technically involved and so on. Well, this system is minimal, so it would be actually really good for that kind of population. Okay, so that just to show that this low-level stuff, you know, does work in somewhat real environments. And I might do, you know, Stepbystep build cooperative robots that way. And I'm not yet decided. Last year I did that exercise. It's a somewhat demanding paper, and I'll figure out whether we actually do that or simplify it a little bit, because it was very hard as an exercise last year. Okay, so that's, I'll have another module right after this. So to conclude that part, see, that's literally just the low-level version of the attractor dynamics that we just had, right? So we can replace the symbolic approach, I mean, these objects in the world that contribute by just having sensors immediately define contributions to the dynamics, but we have to make sure is that the dynamics that emerges is invariant under the dynamical variable. So that you know, the curve, in other words, the dynamics is that function, right? That function is invariant under moving along that function. You know, when we compute it based on sensory information that is obtained at different points in that function, right? If that's not the case, then the dynamics doesn't really tell that, it doesn't really control the behavior, because at every heading it's a different dynamic, so it doesn't really tell you what the heading direction, the rate of change of the heading direction is. So here, that means, for instance, here it's not actually the summing of the individual contribution that is like summing of different obstacles, is that only that sum that has that property. Now, I want to show you a different implementation, which we actually did a little bit earlier, which is a little more abstract and actually very, very performant. And that sort of shows a little bit how so it's a little less naive, and it's a bit more complicated, but you can wrap your head around it. And that sort of shows a little bit the spirit, or I think it helps us to deepen understanding what this idea is of using the attractors to structure behavior that itself is actually then temporally complex and entails transients. So in this earlier work, we did something with an even more radically simple robot. It's we built the hardware ourselves, but it is electronically, it's actually the Lego robot that is the electronics, and you can buy that now. Lego has, it's called Mindstorm, I think, has a toy kit. It was originally a tool. It's a processor, an 8-bit processor, like I always say Coca-Cola machine, kind of very, very simple processor. And the MIT Robotics Lab had produced some public domain software for that. It was called Interactive C. So you could program that. It had like, I think 150 lines of code were possible on that processor, which had maybe a few kilobytes of memory. It was very, very trivial. And that software, I mean, it's a little bit updated, but that's actually what's on the Lego robot. The MIT group made a contract and they made it part of the Lego robot. And at the time, this MIT thing was a lab course where people would be playing with that. I don't know if that's still available as such. Now it's probably just Lego. So we took that. So this is just the batteries and these cables. Like we did a little circuit to condition the sensor signals. Here you see the sensors. So this thing here is the light emitting diode, and this little rubber around it that sort of gives it focus, that the light goes only in certain directions. And this is the detector. So this detects infrared light. There are only 5 such distance sensors on this robot. And so we operate each one in sequence. So this one sends out light and that one, so that there's no interference between those different ones, because the light could be reflected also often other directions. So so each of those is 1 unit of measuring the amount of reflected infrared light, while the target aspect comes from these 2 sensors. This is simply a light-dependent resistor, LDR, pointing, so getting light from a very broad angle in front. Actually, there's literally some Lego here to mount this a little bit higher, so it looks a little bit above obstacles. And all these wide cables are really just the processing sensor signal, the little circuit that turns these on in sequence, and just some preamplification and so on. And then on this board somewhere is this MC something, this chip that is in there. And we have very simple motors. The motors were actually like toy plane motors, servo control motors. We took off the servo part by just cutting the wire, so that we just gave raw voltages to these motors, and the amount of action also depends on the resistance. So if you run this on a carpet, then it runs more slowly than if you run it on hard floor. And so two motors on the two sides is, again, not well calibrated. What you need is that the miscalibration is such that it doesn't, that the errors accumulate slowly enough, then the connection to the world through the sensors will be enough to compensate for any errors. So on this vehicle, we took as the behavior variable not the heading direction itself, but the turning rate. And ultimately, the reason for that is essentially the target contribution. And I'll show you how the obstacle, because we have the same obstacle sensor. So I just showed you that with these kind of obstacle just distance sensors, we can use heading direction as dynamical variable and direct these repulsive force splits. But how do we find out about a target? That's was cheating the previous one. This one would not do good dead reckoning. So we use essentially the Breitenberg kind of idea that if there is more light on the right than on the left, then we turn right. If there's more light on the left than on the right, then we turn left. And this way we would always turn two light sources. You could do that with microphones as well for sound sources. And so in that case, you don't really know where the target is. You actually just know in which direction to turn, if it's to the right or to the left. And therefore, to take the derivative of the heading direction as dynamical variable, the turning rate, then we could set an attractor. We would say we have some default turning direction to the left or to the right for the target. And now we just need to translate the obstacle avoidance constraints into turning rate constraints. So the idea would be if there is a obstacle, for instance, on the right, then and the obstacle is closed, then we make a turning rate that turns the vehicle to the left and vice versa. And when there is no obstacle detected, then we just give a turning rate of 0, which means driving straight. So I'll go through that step by step. So here actually I'm starting now with the obstacle contribution. And so omega is, theta dot, so it's a turning rate, right? And now we have a dynamic system of omega. So this would be the angular acceleration, right? It's the derivative of turning rate, which is the angular acceleration. And so what we're doing here is actually a pitchfork bifurcation. I'll explain that in a moment. But we add a constant. It's this funny way you'll see in a moment why we have pi half. It's really here where the sensor data is here in the alpha, and for some reason we do that, and also explain that term in a moment. And that will be the way of how we give the system a bias to either turn right or left, depending on where the obstacle is. So that breaks the symmetry in a way, while the pitchfork here would be symmetrical. You would always have just as much an attractor to the left as to the right. So this pitchfork, I have a better slide here. This pitchfork here will essentially make the difference between not turning and turning. So just that term itself would switch from having an attractor at 0 when there's no obstacle. Now there will be alpha negative. Remember the pitchfork, where they have a 0 attractor at 0. And when there's an obstacle, then you have a repeller at 0. And let's say this one, sorry, repeller at 0 and attractors at either turn to the right or turn to the left. And that will be symmetrical, that is, you could turn either way. And with this constant, what we're doing is shifting this, breaking the symmetry. So when we shift this up, we're favoring the turning here to the right. And I haven't shown that when we shift this down, then we would favor turning to the left. So when we detect that there's more obstacles on the right, we could favor the system to turn left and vice versa. And again, I'm sometimes confusing left and right here because of the direction of the axis. So here, just shows the shifting upwards to different degrees. So for instance, so what happens here is really there's a tangent bifurcation on top of the pitchfork, right? So when you're in this regime of the pitchfork, then you see now this repeller and that attractor collide and lift off, and that's how you will be turning to just a unique answer of turning to the left, which is this turning rate, and vice versa. If you push this down, you have these something here colliding and just this attractor on the left remaining. Yeah, so step by step, Obviously, if there is no detection of an obstacle, that's what you want. Go straight means turning weight attractor at 0. If you have an obstacle, you want a repel. In these cases, actually, I already explained that, so I don't really need that. Just okay. So that's how we mathematically do this. So mathematically, we can use the force sets that we're familiar with. This, right? This is from the approach I just reviewed. That is an obstacle force that of this form as a repeller in heading direction now. And now we need to lift that in terms of derivative. And so what we do is that we use this form to change the sign. So when we're here in this part, we will shift this up. When we're in that part, we will shift it down. It will be negative. And that's, and this is being on the right of the obstacle, and that's being on the left of the obstacle. So, or the other way around, it doesn't matter. So there you see where we can use this to shift this up. To break the symmetry, shift this up and down, we're using the sign here of the force set. So that's for every sensor we'll add across the sensors. Now here, adding across the sensors. So this just repeats what I just showed from this approach. The other term here in front is also to decide whether we have this at all, and that's controlling also really whether which side of the pitchfork we are. So if there is no obstacle sense, then we want the pitchfork to be in this regime, right? So alpha omega, this alpha negative. And so we can use the same function, namely if I have a single contribution to an obstacle, from obstacle sensor, we can compute the alpha from essentially determining where this is non-zero. Where this is non-zero. So for instance, concrete, we're doing that, we're integrating over this. This is here the integral of that. That is, if I take this, we call this potential here, take the derivative of that with respect to heading direction, then I get that, right? Initially, the slope, it's minus the derivative of that. So if it's increasing, that means a negative here, and then it's 0 here on top, and then decreasing, minus of that gives you a positive value here. And then we just apply a sigmoid. The sigmoid was chosen as arctan for some reason. So we couldn't use other sigmoids. So the sigmoid just makes that we sharply, where 0 crossing, we sharply set that to be the region where where an obstacle is detected. So when we've done the sigmoid, then we have this part is where we want to avoid the direction because there's an obstacle somewhere here in the middle, and that's literally the alpha we'll use. So we'll make the alpha positive and therefore destabilize going straight whenever our heading direction falls into that. And then everywhere else we have a negative value. This is negative, and then we'll be back to this form, just an attractor going straight. That's for every obstacle contribution. So you just sum across these contributions and get this dynamics going. So if you're approaching an obstacle, what would be happening is that initially you're far, and therefore you would have this attractor, because being far means that essentially this is all 0. And could translate here to minus. And then as you get close enough, you can have 3 cases. There would be a case where you write it's symmetrical, right here in the middle. That will be where through this here, these 2 terms cancel. This is 0, and then you get the raw pitchfork here. And so then you have a repeller at that, and it doesn't matter. You can go to turn it to the right or turn it to the left. And then you have this whole region where you know that you want to avoid it to the left, I think. So that's where you will add something to the dynamics. And this is where you want to do the opposite. So you shift it down, you will have only this attractor. And if you're far enough in angle, then you will again have only, go straight. There will be no contribution, and you go back to the original version of the pitchfork. So this is now not happening as you move, but as you turn. As you're turning, this axis is omega, different ranges of omega then go through the bifurcation. I'll go through that again when we have everything added. The target acquisition is kind of trivial. we have only two sensors, left and right. There are multiple ways to do that. And a very simple way we did is that we just say that the attractor in terms of turning rate is a function of the luminance these sensors sense. So if it has a lot of luminance, the votes for a turning in that direction. So that has a height. The attractor had a high turning rate, and the other one has less luminance, smaller turning rate, very broad sinus function, I think, or it was linear function. No, it was, I think that maybe it was a Gaussian, I don't remember the functional form. And then the sum of these two would therefore be biased in the direction where there's more light. And for instance, here you have a positive turning rate. This would be the symmetric case where there's pretty much a zero turning rate. That's the for target orientation. This is the function form. It's a linear term with a Gaussian on top that makes this sort of fall off that way. So the left and right sum. So one could have done that differently. For instance, you could have modulated the amplitude of that as well, with light intensity. And we played with that. I don't remember why we did it this way. So that works here. This is this chip, right? 32K RAM. So it's pretty, probably you've never seen a chip as simple as that. That's, I think I explained everything. And it worked. And I'll show you now. This is a recording. I'll show you now this room where it goes around. We'll see that. Here's a little video. And these are the light sources. It's kind of hard to have phototaxis when you don't have a darkened room. All these obstacles. This is Estelle Bishop actually in Marseille in our lab. And she also acts as an obstacle, but she wants to get out of the way. So it runs around, just obstacle avoidance. Runs around. And so just will turn. Now it turns on the light. The robot doesn't really sense that yet. It's too far from that. So it's heading there just because of the obstacle avoidance. And as it comes around the corner, the lights, I think, yeah, now suddenly the gradient, it turns to the light source there. And actually we also control the speed. So when this was bright, it would stop. And see, that's how she switched on the other light, and now it's some random stuff, and finds the opening, and then she turned it back on. So I didn't explain how the speed was controlled. This is also a very simple equation. So this was only like 100 lines of code and very compact. The code just numerically solved the equation on the robot, and there it switches. Yeah, it's quite agile. We ran this at it wasn't really formal competition, but it was a workshop where everyone used different approaches on very simple vehicles. And then we had a real catastrophe in the last day. We had some press people joining us, and that meant that we all let our robots run in the ground floor of that building. Well, previously we had worked in different rooms, and a lot of the approaches are not really invariant under change of environment. So the robots failed quite badly. And ours was the most robust. It really just ran along just fine. Yeah. Okay. And so if you think through that, why does that work? How does that track the attractor? Now you have to think sort of 1/3 higher. That is, it is tracking the attractor in turning rate. So as it is turning, the rate at which it's turning is in an attractor, and then as it is turning, there's a bifurcation, and then goes to a new rate. So the instabilities happen while it is turning. So when it's going straight, there isn't any it's sitting in the attractor of turning rate 0. Well, that sort of makes you think a little bit more deeply how this really works. So it has a couple of advantages. I told you the original motivation was to deal with these, this qualitative target. You just know target information. You just know is the target to the right or to the left, more likely. And this is a way to implement that. It's not the only way to do that. It also turned out that this makes a very agile kind of robot. And then we made a comparison in a different project here in Bochum, many years later, where we tested out different approaches in simulation. This was actually for drones, but this is only simulation. So we simulated drones flying in a plane and avoiding obstacles. And in a drone, you're interested in not accelerating too much because all of these accelerations cost energy and you want to minimize that. And we compared a couple of approaches. These were sort of potential field kind of approaches. This was the first order attractor dynamics approach, and this is the second order attractor dynamics approach. And you see that it actually had quite different average angular acceleration. There's something about the sign I didn't explain here. And so that is an argument for that. It creates, in a sense, the smoothest behavior. Okay, so that closes this part of the lecture course where we talk about this very simple low-level behavioral dynamics. So behavioral variables was just heading. Again, in all of these robots, there's actually the second variable, speed, which I didn't explain, but it will be in the papers that you have a chance to read. And we create the dynamics from attractors, attractive forcelets versus repulsive forcelets, and the bifurcations to the decisions. And it can be made with minimal perception when we do the subsymbolic approach. So next week, I will put this a little bit into perspective by comparing it to a lot of other approaches of obstacle avoidance. Not a complete survey, I mean, there's a long literature on that, just a few sort of give a flavor for how that's usually done, then we can position our approach a little bit better before I'll actually turn to the aspect of navigation, that is of knowing where you are, which is also very important in all of this vehicle work. Okay, so that closes today's lecture.